I'm Kazuhiro Kurita in Japan. Today I would like to talk about finding the anticover of a string. Uh, this is a joint work with my Alzheimer, Alessio Conte, Shuhen Dezumi, Roberto Grossi, Costa Pros, and Kunihiro Wasa. Let's start. Oh, wait. Okay. In stringology area, periodicity is well studied in combinatorial on words, pattern matching, data compressions, and automata theory. The following structures are well studied: power, antipower, and cover of strings. The power of a string is a string consisting of k concatenate of the same string. Thus, it is a string that continues the same string k times. Moreover, the antipower of a string is a string consisting of k pairwise distinct strings.
Sorry, may I interrupt you?
Yeah.
I'm Gabriele Fici, sorry. You should mention that an antipower is a concatenation of k pairwise distinct strings of the same length.
Sorry. Yeah, so you mean the definition is long?
Yeah, the definition as you have written it is not correct.
Okay, thank you. Okay, so antipower is a concatenation of k pairwise distinct string with the same length. Okay, thank you. It means that antipower is a kind of non-repeating string. And in addition, cover for string x is a set of substrings that cover all positions of x. In this research, we define anticover as a generalization of antipower, and we showed that the problem of finding an k anticover is NP complete. So first, we explain the definition of k anticover. Let x be a string and S is a set of position of x. And a set of position S is called k anticover if k substrings starting at ij and ih are different for any j and h, and any position in x is covered. So look at this example. It is a string ABB, AAA, BAB. This string has 3 anticover. So the set of position 1 and 1, 3, 5, and 8. So starting at 1 is ABB, starting at 3 is BBA, and AAA, BAA. So any pair of two substrings different, and all position is covered. So this is 3 anticover. So next, we define our problem. The k anticover problem. So the input of this problem is a string x and integer k. And output is does the k anticover of x exist or not? The practical motivation of this problem is DNA composition. Minch and Popper consider a similar problem, partitioning a string into distinct factors. And but this problem, k anticover problem, allows some overlap. So this problem is a kind of generalization of Minchid and Pollard's problem. Next, we summarize our results. First, we show that K Anticover is NP complete for any K greater than or equal to 3. And next, when K equal to 2, then 2 Anticover can be solved in polynomial time. And finally, we developed 2 exact exponential time algorithms for general K. And so there are polynomial and linear time algorithms for power and K antipower and covers. However, finding K anticover has a big gap because this problem is NP complete. So related works for finding antipower or covers. Antipower of string can be computed in linear time, even if online setting. In addition, computing shortest cover and all covers can be done in linear time, even if online setting. Okay, we explain the hardness result of K anticover. So first, we show the outline of our proof. First, we show the hardness of K equals 3 pattern, 3 anticover. Oh, sorry. Wait. Oh, sorry. I don't know how to back to slide.
Do you want to annotate your slides?
Yeah, I want to back here. Sorry. Okay. Sorry, wait. Where is keynote? Okay. Okay, sorry. Can you see it?
Yes.
Okay, sorry. So, okay, we explain our outline of our proof. To show the hardness, we consider a reduction from restricted 3-sat problem to 3 anticover. In this 3-sat formula, we assume that each positive literal and negative literal appears at most 3 times. It is known that 3-sat still NP complete, even if we add this condition. Let Vi be ice variables. Since the occurrence of each literal at most 3 times, the positive literal of Vi represented by P1i, P1i, P2i, P3i. It's a positive literal. And there's a negative literal is written by N1i, N2i, N3i. And so the outline of our proof is as follows. First, we encode each clause like this. So there is a clause, and we encode the string. And however, this gadget represents a variable assignment. However, this gadget alone may occur incoherence in variable assignment. So it means that some clause says a variable v1 is true, and other clause says that v1 is a false. To ensure that such situation does not occur, we consider another gadget. This is this part. So by concatenating two gadgets, we obtain instance of 3 Anticover. Next, we will explain the detail of the first gadget. So encoding, we explain the gadget for clauses. In our gadget, a clause v11 or not v12 or v13 is encoded like this. So here, star and sharp are special characters. Star is called jury characters. Then, sorry, star represent a unique character. And a character H is different for each clauses. So the role of H is to assign an ID to each clause. And the character sharp is same across all clauses. So now we obtain important observation. So if a substring S contains a star, then there's no substrings identical to S because all jury character is different. So to cover this string, so we can cover like this. We can pick star sharp sharp, this star sharp sharp, star sharp sharp, and H P11 star, H and N12 star. However, this gray H is not covered. So we have to cover this H to pick some position. And so, okay, next. So since Anticover covers all positions, these grays are covered. So to cover these gray edges, we have to pick star sharp 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 H or sharp HH or HHP11. And to discover this H, we have to pick sharp sharp H, sharp HH, or HH and 1, 2. So thus, we pick at least one substring among these three substrings. Because if we do not pick these three substrings, we have to pick two sharp sharp H or sharp HH. So this is control. It is not Anticover. So we have to pick at least one substring. And so now picking HH and 1, 2 implies literal and 1, 2 is true. In other words, picking HH and 1, 2 implies a variable v2 is false. So by solving these three Anticover, we can compute the variable assignment. However, there is one problem. So this variable assignment made in this way sometimes may have contradiction because one clause says that variable v1 is true. However, other clause says that variable v1 is false. So to ensure that such situation does not happen, we consider the following next gadget. So we consider a gadget that ensures coherence of variable assignments. To this end, we design a gadget enforce a V1, a VI. Since each literal appears at most 3 times, we represent each literal as follows, like 1, 1, P1I, 2, 2, P2I, 3, 3, P3I. And this is negative literals, 4, 4, and 1I, 5, 5, and 2I, 6, 6, and 3I. And so we consider the case of Crouch gadget causing contradiction. So in this case, we pick two. So we avoid the contradiction. We designed the gadget enforce. The role of this gadget is forces to either use of all of 11P1I, 22P2I, 33P3I, or all of 44 and 1I, 55 and 2I, 66 and 2Is. Okay, so next we explain how to implement enforce gadget. So to implement enforce gadget, we use two auxiliary gadgets. So one is amplifier, and the other is one of ABC or DEF. So the role of amplifier is to force to use either BCD or both ABC and DEF. And the role of one of is to make it impossible to use both ABC or DEF. So please look at this figure. So the implementation of enforce is like this: amplifier and concatenate, amplifier, 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 and one of. So this one of gadget forces, we have to pick one of 1P1I2 and 4N1I5. So if we pick 1P1I2, then this green amplifier must pick 11P1Y and 2P2I3 because the amplifier gadget use BCD or ABCDEF. In this case, BCD is corresponds to 1P1I and 2. So if we use this one, so we use P1, P1I2, so 2 twice. So it is a it is not Anticover. And next, we have we use 1P1 and 2P2I3. So yellow amplifier is used 2P2I and 33P3I. So one of gadget use this one. So this gadget use all of 11P, 22P, 33P. So we can implement enforce gadget. Okay. And so this idea can be generalized for general K. So by using this reduction, so all K Anticover can be reduced to K sat. So K Anticover is NP complete. So this slide is corresponding to the reduction 3 sat and 3 Anticover. So so assignment is corresponding to the picking substring, and the crowd satisfaction is corresponding to picking at least one from this set of substring, and the coherence of assignment is corresponding to enforce gadget. So this is a summary of our idea. Next, we explain the polynomial time algorithm for finding two Anticover. And so our goal is we give order n times the size of sigma time algorithm for two Anticover. So main idea is reduction from 2 Anticover to 2 sets. So in this reduction, each position of a string corresponding to a variable pi. So clause ci and cn single clause pi and pn, and each clause pi is corresponding to pi minus 1 or pi. However, so a set of a position may be contain two same substrings. To avoid this situation, we add the clause is bij. So the definition of bij is like this. So the role of clause bij is avoiding pick two same substring. Next, we show the example of our reduction. So our input string x is ABB, AAA, BAB. So we can pick a set of position 1 to 10. We reduce to that formula like this: P1, P2, P3, P9, P10, and this part is Bij. This part is so how to say condition for covered. By solving this two-sat formula, we can obtain two Anticover. But so our goal is order n times the size of sigma time algorithm. But the size of this two-sat formula is order n square, because the total size of this green part is n square, because there is any pair of two position can be added in this area. So next, we consider how to reduce the size of this formula. So first, we show one observation. If a string x contains a factor means substring of length 3, that occurs 3 or more times, then x has no two Anticover. So please look at this example: a string ABC, ABC, ABC. It has no two Anticover, because two cover first B, so we pick AB or BC. Okay, and to cover second this B, we pick AB or BC. But so third B, we have to pick AB or BC. But so to cover first B and second B, we use both AB and BC. So we cannot cover third B. So it means that each B plus one another character appears at most 2 times. So this observation implies that each Bij is at most 2 times the size of sigma plus 1 position. Each position I has at most this number of positions. So how to say the same substring occurs. So and so as a preprocessing, we can compute such length 3 substring is this preprocessing can be done in order n time and the size of sigma time. So the size of TSAT formula is bounded by order n times the size of sigma. And it is known that TSAT can be solved in linear time of the length of formula. So we can obtain this time order n times the size of a sigma time algorithm. Finally, we explain the exact exponential time algorithm for finding.
Katsuhiro, I'm really sorry to interrupt you. I don't think we have time for this part, so maybe you can wrap up the talk.
Okay. Sorry. This part is so very simple branching algorithm. So we just follow our results. So first we design this time complexity algorithm. So this idea based on simple branching rule. And next we design this time complexity algorithm. This algorithm is fast when k is very big case. So conclusion and future works. K Anticover is NP complete for any k greater than or equal 3, and 2 Anticover can be solved in polynomial time, and we developed 2 exponential algorithms for k Anticover. And other future work, our reduction use many alphabet. So if the input is constant size alphabet, so maybe there is an efficient algorithm. So we want to consider the constant size alphabet case or parameterized case for parameterized by the size of alphabet. Thank you for listening.
Thank you.